Hello and welcome all to the webinar Increase Spectral Efficiency in Coherent Optical Communication M8190A AWG. Today we will hear the presentation by René Schmogel, who is a PhD student at Karlsruhe Institute of Technology, and Bernd Nebendahl, who is a senior R&D engineer and project lead at Agilent Technology. My name is Dimitri Malsam, and I'll be your moderator and question manager today. For everyone's comfort, this is a lecture-style meeting. However, you can send questions in writing at any time during the session through the Q&A functionality of the WebEx meeting. We'll do our best to answer your questions during the session, but if we haven't been able to. While the answer to your question may be published for others to see, we will keep your identity private. Please be reminded that this webcast will be recorded so you can review and share with your colleagues at it. And now I hand over to Bernd Nebendahl to start the presentation.
Thank you, Dimitri. Today's meeting about spectral efficiency. I will switch over to the first slide now. So the question here is, do we really need more bandwidth? And this is a sketch from the internet traffic at the Amsterdam Internet Exchange over a couple of years. And the overall increase rate was a factor of 1,000 over 10 years. That means every year, roughly the internet traffic doubles at this internet exchange. And the projection, and this is a source from Cisco, is that by 2015, the whole internet traffic will reach 1 zettabyte. That's 10 to 21 bytes. The estimation is that the increase of the traffic will be roughly a factor of 4 over the next 5 years, and that the number of devices connected to IP networks in 2015 will be twice as high as the global population by 2015. So actually, we believe we really need more bandwidth, and the question now is who is really using this bandwidth. And there are a couple of services you can basically distinguish. There are on the one hand the high volume services like the HD TV, video on demand. People talk about quad HD now, 3D TV. There's a lot of downstream traffic on those services. Then on the other hand, there's real-time services like online gaming, derivative traders. And there's a new area of cloud computing, storage area networks, all these services. They all need the high bandwidth. The question now is, we need more bandwidth, but do we need more spectral efficiency? And the answer is quite simple. If you look on a classical communication channel, typically the channels have a given bandwidth of, say, 50 gigahertz. And in the past, people have been using return to zero or non-return to zero modulation on off-keying at 10 gigabit per second, and they were populating the channel not completely. Now if we switch to higher modulation speeds, for example 100 gigabit per second, the occupation of the modulated signal is larger than the bandwidth of the channel that's assigned to it, and there will be crosstalk between the channels. So this is not going to work. You can't increase the modulation speed without increasing the channel width. And so what people have come up with is use different modulation schemes to increase the spectral efficiency. And for example, if you use differential phototrope phase shifting DQ-PSK, you can restrict the bandwidth occupation of 100 gigabit per second signal such that it fits into a 50 gigahertz channel.
So the question is, what are the theoretical limits to spectral efficiency? Well, there's a very famous formula of Shannon, which is called the Shannon channel capacity. We can see that there are basically two ways to increase the capacity of a given channel. The first way would be to increase the bandwidth B. So if you increase the bandwidth, of course, you can increase the amount of bits you can transmit per second. And another way to enhance the channel capacity is to increase the signal-to-noise ratio. Of course, this is very limited in optical fibers because as you increase the launch power into the fiber and hence increase the signal-to-noise ratio, at some point nonlinearities will kick in. So here we can see a plot which shows the information spectral density, so C divided by B, for different launch powers, here indicated as power spectral density. And you can see that the indicated Shannon limit, which is the blue dashed curve here for coherent communications, cannot be followed all the way, because at some point when the power spectral density increases, the information spectral density drops again, which is indicated by the red curve here. The lower two curves, namely the green and the orange curve, are there indicating the limits for direct detection schemes, like on-off keying, for instance. So what does that mean when we look at different lengths of fibers, so different distances? We can see as a thumb of rule, which comes also not surprisingly, if you increase the transmission length, you decrease the maximum spectral efficiency you can get over this channel. And you can see that for 500 kilometers, which is a rather short link, you can reach up to 9 bit per second in hertz theoretically, whereas for a rather long haul application where you have a transmission distance of 8,000 kilometers, you could hardly reach 6 bit per second in hertz.
So the question now is, how can we reach these limits? Because they are physically given, so we can't go beyond the limits, but how can we reach the limits? And if you look at a communication system, you can of course distinguish those into direct detection systems. Typically they are using on-off keying. Sometimes you do radio over fiber, it's not a real digital transmission system. Or you can use multi-carrier modulation formats on direct detection systems. But today we are focusing on coherent detection, and in coherent detection you can of course do polarization multiplexing, which will give you a factor of 2. We will come to that later on. You can do various modulation formats to increase the number of bits transmitted per symbol, or you can do spectral shaping to reduce the occupied bandwidth of your modulated signal. And within the spectral shaping, you can of course distinguish between time domain pulse shaping, so just shaping the pulse in time domain to reduce the spectral occupation of your transmission signal, or you can do orthogonal frequency division multiplexing using multiple carriers. We will come to those two also in more detail later on. Now let's look at the test and measurement tools used to do measurements and to do experiments in this arena. If you look at a very simple transmitter configuration for QPSK, which is quadrature phase shift keying, you have the digital bit stream coming in. You demultiplex this into 2 separate bit streams at half of the rate and put it into an IQ modulator. And this will lead to a waveform for 1 signal on the upper arm and for 1 signal on the lower arm. And so the linear superposition of those two is this wave down here. And it can be depicted by the cancellation point 1, over here. Now, if you have a transition to a different symbol, the 0, 0 symbol down here, the phase of both waves flips to 180 degrees. The same happens here on the superposition. And so the transition depicted in the cancellation diagram, which is basically the complex coefficients of the INQ waveform, goes from 1, to 0, 0. Now going to the next waveform, there is a 180 degree phase shift on the Q channel. There is no phase shift on the I channel, and so on. So finally, you have all 4 symbols, and you see that those 4 symbols can be distinguished by phase differences of multiples of 90 degrees.
So in the previous slide, you have seen a concept for a QPSK, a quadrature phase shift keying transmitter, but how do we get to even more advanced modulation formats like quadrature amplitude modulation? Well, there are several ways to set up one of these more advanced transmitters. There is a way to do it optically, or you could also do it electrically. Let's have a look at the optical variants first. You could always use discrete components by off-the-shelf IQ modulators and align them in the setup, as you can see here. So in this case, a laser source is split up and fed to 2 IQ modulators, where the in-phase and quadrature phase of the signal is encoded onto the laser. And then one of the two arms will have an attenuator in order to create a multi-level signal. In this case, with this configuration, you would be able to create a 16-QAM signal, as you can have 4 signal levels in each of the dimensions I and Q. However, building a setup like this is very demanding, since the phase between the two arms, the upper arm and the lower IQ modulator arm, must be precisely controlled. Otherwise, your signal will look very bad. Therefore, a good way to do it is to use an integrated optical 16-QAM modulator, as you can see on this slide to the right. So in that way, the phase control, which is very demanding in the discrete way, can be much more simplified if you have it all on one chip. However, modulators like this are not commercially available. There have been, some groups have reported on building structures like this, but there is no off-the-shelf component you can buy at the moment. So this is a disadvantage here. Of course, when you go from the optical domain, you can also go to the electrical domain and create electrical multi-level signals and use a single IQ modulator. You can do this again in a discrete way, as indicated here, also for a 16-QAM modulator. Therefore, you use 4 electrical signals and you attenuate 2 of these lines. Therefore, you can again create a 4-level signal in the upper arm after the electrical combiner and on the lower arm. And thus, you can use a standard IQ modulator to encode 16-QAM data onto an optical carrier. This solution offers very fast signals, so you can use standard pattern generators. Of course, you have again to control the electrical phase here, which is much more feasible than controlling the optical phase. However, looking at this solution, it seems very inflexible, since this, if you want to add a bit, for instance, you have to add another set of hardware to generate even higher level signals. Therefore, you could go for an integrated electrical solution. Bernd? Okay, thank you. So use digital to analog converters here, electrical ones, fully integrated. There are digital to analog converters available up to speeds beyond 50 gigasamples per second and resolutions of 6 to 8 bit, and for the lower speed even much more than that, up to 12 bit and more. So this solution is very flexible and very feasible, as all the components are available right now. And this is also the solution we are concentrating on, since this processing and D2A converter part is already included in the arbitrary waveform generator. So another way to increase spectral efficiency, if we have one of these advanced transmitters, is the use of polarization division multiplexing. So when you do polarization division multiplexing, you make use of the fact that you can propagate 2 orthogonal polarizations in optical fiber, which do not see any crosstalk from another in the best case. Therefore, you can encode your 2 independent data streams onto Y and X polarization and thereby increase the spectral efficiency by a factor of 2. So, having looked at polarization division multiplexing, we can have a further look at our advanced transmitter and see what kind of modulation formats we can actually implement and which kind of modulation formats can we use to maximize the spectral efficiency of a given link. So let's have a look at the modulation formats theory. In this setup, we use our multi-format transmitter. We have just outlined a few slides ago. Use a stage which emulates a polarization division multiplex signal. Therefore, we split up the signal into 2 arms, delay one arm with respect to the other, and combine the 2 signals in orthogonal polarizations here at the polarization beam splitter. We can use an optical spectrum analyzer to have a look at the optical spectrum of a signal, here shown for 16 QAM, and we can use a digital communications analyzer to look at the eye diagram of the optical intensity. Of course, if you just look at the optical intensity of a coherently modulated signal like a QAM, you will not be able to recover all the signal information. There, if you want to do so, you need a coherent receiver, which is shown in the upper right, which can be used to decode the constellation diagrams of the two polarizations.
So now looking at an example how the increase of spectral efficiency is shown in the spectrum of the recording signals. So from the bottom to the top, we are starting at 112 gigabit per second non-return to zero and off-keying signal, and showing how wide the spectrum would look like compared to a 50 gigahertz ITU channel width. Then we introduce a factor of 2 in terms of spectral efficiency when going from return to zero, non-return to zero and off-keying to QPSK. So the spectrum is narrowed by a factor of 2. Then we add another factor of 2 for polarization division multiplexing, so that we end up with a spectrum that's 4 times narrower than the original one, finally fitting into a 50 gigahertz ITU channel. So that's why the polarization division multiplex QPSK signals for 100G actually fit into a 50 gigahertz wide ITU channel. So looking at modulation formats, we just have talked about QPSK being 2 bits per symbol. We can basically line up the modulation formats that are used in coherent communication. So starting at 1 bit per symbol, BPSK stands for binary phase shift keying. The constellation diagram just contains 2 constellation points, meaning that we can just transmit 1 bit encoded onto the actual points in this constellation diagram. Next complex modulation format, QPSK, having 2 bits per symbol. The constellation diagram looks like a square. We can continue the row, looking for signals that have 3 bits per symbol. So we need 8 states, 2 to the power of 3, to encode 3 bits on the symbol. So there are 2 variants. It's the 8PSK, which stands for 8-fold phase shift keying, or the 8QAM, which is a variant of this, having a slightly different constellation shape. Now for 16 QAM, there are various choices. You can go for 16 states, 4 bits per symbol. You can go to 16 QAM, which is just a square with 4 levels in each direction. Or you can use 16 APSK, and there's 4 states in the center circle and 12 states in the outer circle, taking advantage of better use of makes better use of the actual available optical power. Or you can use a 16 star QAM. However, in the center ring, you have, of course, quite narrow spacing between the symbols compared to the outer states. The same is basically available for 32 QAM. It's a 6 by 6 square where you just omit the outer 4 corners, so that you end up with 32, which is a power of 2 again. You can do a 32 star QAM or 32 APSK, where you have basically 3 amplitude levels and different number of states on the individual rings. Now, if you continue 6 bits per symbol, it's a 64 QAM. It's 8 by 8, 128 QAM. It's again a non-square format because we need to have a power of 2 number of states. It's a 12 by 12 where we omit also corner states. Can continue this to 256 QAM, 512 QAM, and even QAM 1024. That's something people in RF have been using so far. Now, if you look at measurements on the modulation formats, when we have done these using the AWG, we start with QPSK. The spectrum is also shown on the right side. This is a spectrum for 3 gigabaud symbol rate. Now, if we switch from QPSK to 16 state format, we have 2 examples here. It's a 16 QAM on the left side, and it's a 16 APSK on the right side. 4 bits per symbol in this case. Now 32 QAM, 32 APSK, 32 states, and the spectrum always stays the same. 64 QAM, spectrum stays the same, and QAM 256. So there's no change in the spectrum. And the message here is that regardless of the actual number of bits per symbol, the bandwidth occupation for formats is the same for all of those.
So let's have a look at the measurement setup we have used throughout all the measurements presented in this talk. So for the transmitter, we have used the AWG to drive an optical IQ modulator with multi-level electrical signals. We have used the narrow line width laser source, for instance, an external cavity laser, to be encoded by the data. And then we have used the previously introduced polarization division multiplexing emulation stage here, where we split up the signal and combine them in orthogonal polarizations with an introduced delay. Then we amplify the output signal, transmit over a wanted link of fiber, and then for the receiver we use a preamplifier here, indicated by the erbium doped fiber amplifier, and the coherent front end. So let's have a look at the spectral shaping. There are basically two ways to increase the spectral efficiency by spectral shaping. One is the time domain based pulse shaping, and the other one would be orthogonal frequency division multiplexing. So let's first have a look at the time domain pulse shaping and at the theory of this time domain pulse shaping. So let's look at the extreme. What is the minimum bandwidth we need to transmit data? Well, Nyquist tells us what kind of bandwidth that is, and how do we get there? We could get there by transmitting orthogonal sync-shaped pulses and encode the data onto these sync pulses. So, and looking at the Nyquist theory, we know that the pulse spacing, so the time between two adjacent pulses, indicated here by TS, and the minimum spectral width of the signal, they are related exactly by TS equals to 1 over Fs. So if we look at the waveform here, as an example, there are 3 sync-shaped pulses. They are orthogonal in that way that each maximum of each sync pulse falls onto all the 0 crossings of all the other pulses. So they can be received without anti-intersymbol interference. And the time between 2 adjacent pulses is indicated here by TS. So if we look at the spectrum, we find that the spectrum is confined to a rectangle, which has the boundaries minus Fs over 2 to plus Fs over 2. So the width is exactly Fs, which is 1 by Ts. And we can see that for each of the sync pulses, we find a spectral harmonic within this rectangular spectrum. And the harmonic is introduced by the temporal displacement of each of the pulses. So each temporal displacement gives you another spectral harmonic within the rectangular shaped spectrum. So in real-world applications, we cannot really construct sync pulses as they are by definition infinitely extended in time. Therefore, we have to use an approximation of these sync pulses. And we try to do so by using finite impulse response filters of order capital R. So the higher the order, the longer the filter is. And we have also to introduce an oversampling by a factor of Q here, because we have to deal with sampled signals, and sampled signals show periodically repeated spectra. And in order to use feasible anti-alias filters to reconstruct the analog waveform, we need to have a separation between the periodic repetitions of the spectra. Therefore, we introduce a factor Q. Throughout this talk, the oversampling factor Q will be equal to 2. However, if you use if you use appropriate filters, you can reduce the Q to lower numbers approaching the limit of 1. So if we have a look at the typical non-return to zero signal pulse here, which is a rectangular pulse. We can see what this corresponds to a filter order of 0, so no filter basically. We can see the spectrum in a linear scale is spills into the frequency band outside of the minimum FS band defined by the Nyquist theory. So the FS is located between the -0.5 and the 0.5. Now if we look to the spectrum of simulated data, we find that this theoretical linear plotted spectrum here nicely fits into the power spectrum of the simulated data, which is the white line located inside of the noisy curve here. So if we now use an FIR filter to approximate the sync pulse, we have to introduce a time window because we cannot do infinitely extended pulses with a finite impulse response filter. So here we show a filter of order 16. So we can see that the ideal sync impulse is truncated. And of course this has an impact on the output spectrum. If we look at the spectrum now, it is not the ideal rectangular spectrum, but it is distorted by this rectangular window. And if we have a look at the power spectrum of the simulated data, we can find that a lot more power is located inside the Nyquist band. Nevertheless, still quite a good portion spills outside of it. So what can we do about this? We can increase the filter order to better approximate the sync function. So if we go for a filter of order 32, you see that the sync function is approximated better. Therefore, the resulting spectrum approximates also an ideal rectangular better. Nevertheless, we still find these ring artifacts. And if you look at the power spectrum again, you see that the signal spectrum evolves towards an ideal rectangle. And if we choose a very, very long filter, indicated here by a filter order of 1024, we can see that the spectrum is almost an ideal rectangular, You can still see the ringing at the steep edges, which is also called Gibbs phenomenon. And you can see the corresponding power spectrum, and almost all of the signal power is confined to the Nyquist frequency band. So this filter is very close to ideal. Of course, if you don't want to get rid of these ringing artifacts, and if you want to get a better out-of-band suppression, you can use raised cosine filters. And we've already shown the limit of these raised cosine filters, which is the sync-shaped filter. So for raised cosine filters, we identify the roll-off factor, alpha here, as the key parameter to characterize the final filter form. So the sync function we have shown on the previous slides corresponds to a roll-off factor alpha equals to 0. Of course, we can increase this roll-off, here indicated by the black, the magenta, and the red curve. And as the roll-off factor approaches 1, the ringing to the left and the right of the main peak decreases, and the decay is increased. And if we look at the spectrum, the corresponding spectrum, we find the best approximation of a rectangle, as outlined before, is alpha 0. If we choose alpha 0.05, we are still very close to an ideal rectangle, and at the same time get rid of the ringing artifacts at the steep edges. If we increase alpha further to 0.35 or even to 1, we can see that again more signal power spills into the frequency bands outside of the minimum band defined by Nyquist.
So now we have heard about the theory and the mathematics behind it, and we are going to show a couple of measurements now where we have really applied these pulse shaping with the help of an AWG to an IQ modulator or signal that was then encoded onto an optical carrier. And we are starting with a non-shaped, basically, pulse, a rectangular pulse in that sense. So the spectrum shows these characteristic side lobes. The eye diagram here in the center is typically for a wide bandwidth signal, so you have pretty sharp transitions and wide-opened eye. And in the constellation, which is just a visualization of the complex content of the signal, you have the constellation points and more or less straight transitions between the two consecutive or neighboring signals. Now, if we switch on to a raised cosine filtering of the time domain signal, here with the roll factor of 1 that has been discussed by René just a couple of minutes ago, you see that the spectrum is starting to narrow. The side lobes, the characteristic side lobes, are basically not visible anymore. The eye diagram still has pretty wide eyes, pretty wide open eyes, and constellation looks very nice. As you can see, the constellation points seem to be smaller, and the reason for that is that for detecting this signal and the narrow bandwidth signal, you can basically also narrow down the detection bandwidth of your coherent receiver, which allows you to reduce the noise in your system. So basically you get an advantage in terms of noise if you use less bandwidth in the detection scheme without the penalty of having some inter-symbol interference by using too low bandwidth, because the signal has low bandwidth in itself. Now, continuing the row to raised cosine with an alpha of 0.35, you can see that the spectral width is decreased even more. Now you start to see characteristic overshoots between the transitions. At the constellation point here over here, or in the constellation down here, you can see that the constellation points are hit perfectly, but the transition seems to be chaotic, but this is actually an effect of the using the raised cosine filtering. This leads to overshoots and undershoots in the transition, but still you keep the same constellation points. And ultimately you can go to alpha 0.05. You can reach almost perfectly to a rectangular spectrum. The transitions are even more distorted, or overshoots are more visible, but still you can hit the constellation points perfectly in this scheme as you have seen before. So reducing the bandwidth allows you to reduce the noise. So low bandwidth is lower noise. Overshoots are present, but if you sample at the right point in time, you still can get very nice constellation points.
So having talked now about time domain pulse shaping, we have already mentioned shortly that there's another way to increase the spectral efficiency, namely by using orthogonal frequency division multiplexing. So orthogonal frequency division multiplexing has become very popular in optical communications over the last few years. So let us just have a really short repetition of what OFDM, or orthogonal frequency division multiplexing, is all about. So you start off in the frequency domain. Here shown 4 carriers at 4 different frequencies. They are all equally spaced in the frequency domain, and you encode the data onto each of these carriers. So in this case, the blue, the green, and the red carriers are multiplied with a coefficient 1, and the orange carriers multiplied by coefficient -1. So if you want to obtain the time domain waveform, you perform an inverse fast Fourier transform, and you can see that for each of these 4 carriers, there's a corresponding time domain waveform. And the output signal is constructed from the superposition of all these 4 carriers in this case. And you can see that for the blue, the green, and the red carrier, there is no phase shift, so the phase is 0, corresponding to a modulation coefficient 1. And for the orange one, the phase is shifted by 180 degrees, which corresponds to multiplication by -1. And the compound signal is seen at the bottom, which is the black curve. Now at the receiver, you have to do the inverse operation. In this case, you use a fast Fourier transform, and you can recover the data modulated onto each of the 4 carriers. You could also use also perform a down conversion with an LO, so you use a mixer and integrate over one symbol period, and that way you can also extract the information carried by one of the subcarriers. And you can again see here by the response of the fast Fourier transform that you can see spectral sinc functions located around each of the 4 carriers, and you can again see the orthogonality by the fact that each of the peaks or each of the carrier positions or the other functions or other sinc functions cross the 0 line.
Now again, after this short introduction into the theory of orthogonal frequency domain multiplexing, we are going to show a couple of measurements. We have generated the waveform again using an AWG, same setup, just different waveform to the AWG. And we have chosen an OFDM signal that consists of 15 subcarriers. On the data subcarriers, we have used the QAM16 as a modulation, and we have added 2 pilot tones to simplify the phase reconstruction or the phase estimation. And so finally, you end up with the time domain waveform. That's what René has shown in black here. The spectrum for 15 subcarriers looks like this. You see that there is a fairly flat portion of the spectrum which is consisting of the 15 subcarriers which carry the data and the pilots. And there's a more or less steep roll-off to the sides. And so by increasing the number of subcarriers, you can also increase the roll-off, and you can approximate the rectangular spectrum for a higher number of subcarriers. So in this case, we have 31 subcarriers. Again, we have 2 pilots. So the number of pilots, which is basically an overhead to data transmission, is of course now reduced. And continuing this to 63 subcarriers, you can see the pilots in the center, and the spectrum is almost rectangular now. And finally, measurement with 127 subcarriers, the spectrum is approaching the rectangular shape almost perfectly, and the actual spectral efficiency is approaching the limit almost perfectly now in this case.
So we have talked now about both the time domain pulse shaping and orthogonal frequency division multiplexing. Now let's have a comparison between the efficiency of these 2 techniques in terms of spectral or achievable spectral efficiency. Therefore, we have plotted here the possible spectral efficiencies normalized to the logarithm of m, where m is the number of constellation points. So we have normalized it to made it independent of the QAM format you're actually using to compare both. And on the x-axis, we have plotted for OFDM the number of subcarriers, or in this case the IFFT size, which is equivalent, capital N, and the filter length or filter order we have used to create the Nyquist sinc pulses. And you can see that both techniques more or less perform the same. So it doesn't really matter if you're just looking for high spectral efficiency, whether you use OFDM to achieve this target, or you use Nyquist time domain pulse shaping. Sorry. However, looking at another characteristic of these signals, namely the peak-to-average power ratio, which was often reported about when talking about OFDM, and that the PAPR is a very high disadvantage regarding OFDM. We can see when we compare the 2 signals, or the 2 time domain waveforms, we can find that for OFDM, the PAPR is a much bigger issue than it is for the time domain pulse shaping.
Okay, so now let's take a closer look onto the actual measurement hardware we have used during these measurements and during the presentation. Of course, the key instrument to do all this construction of waveforms in the time domain, whether it's time division, orthogonal frequency division multiplexing, or time domain pulse shaping, is an AWG. And we have used the Agilent M8190A that offers 14-bit resolution for 8 gigasamples per second, or 12-bit resolution for 12 gigasamples per second. There's possibility to have 2 channels per module, which fits nicely to an IQ modulator, for which you require the 2 channels to drive the I and the Q waveforms independently. There's a direct D to A converter output with an output swing of up to 700 millivolts peak to peak. We have used a direct D to A converter output because this one offers the best linearity compared to going over an amplifier that would, of course, drive the modulator a little bit further, but you, of course, lose a little bit of the linearity of the D to A converters. You can find more under this link, and I think this link will also be posted to the attendees later on via mail. Software-wise, the AWG can be controlled via Skippy commands or through an IV COM driver. In this presentation, we have used MATLAB to create the waveforms, because this is the most flexible technique, of course, to do all kind of new signals and different signals. There are, of course, other software environments available from Agilent to create signals, like Agilent Signal Studio or SystemV, which is a system simulation environment, and of course it's supported by the Agilent I/O libraries. On the receive side, we have used the optical modulation analyzer. As we are leveraging the vector signal analyzer software from the RF domain, we already have all the modulation formats that we have shown throughout the presentation. And beyond that, we have other modulation formats. In particular, we have just recently introduced a custom APSK, amplitude phase shift keying decoder, where you can tailor your decoder to the signals you want to look at. You can specify the number of rings for your APSK format. You can specify the ring ratio, and you can specify the number of points on each ring. So you basically can construct the ideal signal for an optical communication link and measure this using the optical modulation analyzer. And in addition to that, the OFDM signals we have presented here were also measured by this instrument using a custom OFDM decoder, where you can configure your decoder in terms of preamble, pilots, data, and sample frequency. There's much more available to configure the OFDM decoder, and this is a fairly complicated system, but we do have pretty much all you need to do any kind of OFDM signals. Software-wise, we have used MATLAB for signal generation. We have built a small interface to create the OFDM signals. For example, this is the tool to generate the OFDM signals, and with the same tool, we can also create the setup files to do the decoding on the modulation analyzer. So it's a complete chain from signal generation, downloading to the AWG, and receiving the signal, and setting up the decoder on the OMA to receive the signals. So to summarize, we have started to characterize the optical communication systems. We have concentrated on coherent detection. We have briefly touched polarization multiplexing. We have shown a couple of modulation formats. We have shown spectral shaping in 2 flavors. First, time domain pulse shaping or Nyquist pulse shaping to increase spectral efficiency by reducing the bandwidth occupation of your signals. And we have shown orthogonal frequency division multiplexing, basically doing the same, reducing the occupied bandwidth, but using a different approach. Here again, the modulation format overview, starting from BPSK 1 bit per symbol all the way down to QAM 1024 with 10 bits per symbol. We have shown a couple of measurements for QAM 16 signal, going from rectangular pulse shaping to raised cosine with a roll-off of 0.5, showing the dramatic reduction of bandwidth occupation of the signals. We've shown the same for OFDM signals, reducing the bandwidth occupation or narrowing the spectrum when going from 15 subcarriers to 127 subcarriers. This is again the block diagram. Actually, this is not only for Nyquist pulse shaping. The same block diagram works for OFDM. It's just a different waveform from the AWG. The measurement hardware is identical for both type of measurements and both type of signals. And finally,
yeah, if you're interested in some literature about the topics we have briefly covered today, there are several papers. So most of it was concerning the time domain pulse shaping, for example, the influence of finite impulse response filtering, and also the comparison of spectral efficiency and picture average power ratio can be found in this Optics Express, which is going to be published pretty soon. It's going to be the volume 20 for the first issue coming up next year. Then there will be a talk at OFC next year about real-time generation of these time domain pulse-shaped signals. And there are some other publications on OFDM and how to enhance the speed when going from AWG studies to real-time operating systems. And finally, I think pretty interesting topic, which is the error vector magnitude you can use as a performance measure to judge the quality of your signals.
Okay, and finally, of course, there is also literature available from Agilent. There are a couple of white papers, data sheets. There's a webinar series that is available on download on the Agilent website. And of course, there is information about the AWG, the OMA, and also about the oscilloscopes.
Thank you very much, Bernd and René. As mentioned, this is the time for question and answers now. You can send questions in writing through the Q&A functionality.
Sorry, there was a mute in the signal. Thank you very much, Bernd and René. As mentioned, this is now the time for questions and answers. You can send questions in writing now through the Q&A functionality of the WebEx meeting, and we will do our best to answer your questions during the session, but also may come back to you later after the session if we haven't been able to. While the answer to a question may be published for others to see, we will keep your identity private. And starting off with the first question that we had, talking about spectral efficiency in general, what is the record at the moment and how it is achieved? The record lies at 13 bit per second in hertz, achieved by time domain pulse shaping, and I think René can comment a little more on that.
Yeah, this experiment has been demonstrated at last year's ECOG by the group of Professor Nakazawa, and he managed to transmit a 512 QAM signal shaped by a raised cosine filter over 150 kilometers of fiber.
Okay, thank you. The second question posted was, can pulse shaping be performed in RF optics domain or RF/optics domain? Did anyone try to do this? So it's open to both of you to take it?
Yes, so there is work by several groups who use, for instance, wavelength selective switch to perform the pulse shaping. One was done that I was just looking for the reference, was published in an Optics Express. I just have to find it real quick. Yeah, the paper is called Ultra Dense WDM PON Delivering Carrier Centralized Nyquist WDM Uplink. It's by the group of Professor Chang. So I can provide the link to this paper if you're interested in how people or how groups have done optical filtering of the standard non-return to zero signals. To my knowledge, in the RF domain, so using electrical analog filters have not been demonstrated so far.
Okay, thank you, René. And we will add René's link to the list of publications into the email you'll be receiving after the webinar. Another question's popping in. Looking at slide 30, time domain pulse shaping, the raised cosine with alpha 0.05 seems to be the most efficient way in terms of spectral efficiency. And as nothing is for free, what would be the implications of it? Bernd?
Yeah, maybe I can start to answer this question. I switched to this slide 30 again to have this for reference. As you can see, if you look in the eye diagram, and that's why we have inserted them also here, is that when going from rectangular shaping to raised cosine with a small roll-off factor, the eye opening seems to close. So the penalty is basically due to the fact that you have to sample the waveform at the proper time. The eye opening is very open at the right sample point. If you deviate from the right sample point, if you get the clock phase wrong, then of course you are going to see a smearing out of the constellation point, and René maybe can also comment on this one.
Yeah, so the impact of not having the right, exact right sampling point has been investigated, and also an algorithm to find this optimum sampling point has been demonstrated and discussed in the reference number 1 I have shown you. Can you go to slide 50?
Yeah.
So the upper reference, so there we have had a look at the impact of not hitting the sweet spot of the constellation diagram, and also introduced an algorithm to find the sweet spot with a in a very reliable way.
Okay, thank you for that. No more open questions in the chat, I see. So we still have some time to react on the questions. If you have any questions after the event, please don't hesitate to contact us on the address mailed to you after the webinar as well. Okay, so seems to be clear. I think it was very informative so far. And at this point, I would like to thank you all for your participation. And within 24 hours after this webinar, you will also be provided with the link to the recorded session to be shared with your colleagues. And this email will also contain complementary information and resources like the publication list we showed you previously. When I closed the session in a few seconds' time, an evaluation form will pop up at your screen, and we do appreciate your feedback and comments on the webinar. It will help us to improve the following sessions. So thank you again for your attendance, and I wish you all a nice continuation of your day, and I hope Merry Christmas.